Okay, good morning. Welcome to COMG 302 Research Methods, Week 2, Lecture 5. So, previously we talked about um, what concepts are, what constructs are, and what variables are. We said that variables are essentially concepts or constructs that can take different values exactly because the values that a concept takes can change, can vary. We call them variables. It turns out that this exact process of assigning numbers or assigning values, more specifically, to concepts has its own term. We call it operationalization. So this lecture will be focused on various issues regarding how we operationalize or operationally defining a variable or a concept. Okay? All right, so let's continue to use this formidability hypothesis as an example. It says, the more power a person has, more likely this person will be aggressive. And we said that in order to test this hypothesis, we need, first of all, to, turn a more abstract construct to a more specific one or more concrete one. In this case, we use physical strength. That's, as concrete, pretty much as concrete as we can get. We can easily observe, for example, how strong or how weak a person is. Another important task, of course, is to turn the other concept in this statement, aggressiveness, to another, phenomenon that is easy or relatively easier to observe, and that is how much one is, how easy one is to be angered. We'll call it proneness to anger, right? So again, we can sort of assign a value to this particular concept, turning it to a variable. Um, well, that's exactly what we're gonna do, right? And we sort of talked about the various consequences of assigning values to a concept. That is, we can start to discuss and visualize the different kinds of relationships between two variables and even among three variables or more than that. So as we just said at the start of this lecture, that this process of assigning values to a variable, um, or this procedure we call operationalization. More specifically, it turns out that assigning values to a concept is only a part of this process or procedure that we call operationalization. More broadly, it's how we will specify different rules, right? Another term for this, research procedure will be different rules. How exactly we're going to operate, to phrase it differently, in this research project such that we can obtain reliable empirical observations or to obtain reliable data that we can trust as tests of our theoretical concepts or constructs, right? Very loosely, for the purpose of this class, we can sort of regard or consider this process as this question, right? How do we measure a concept? How do we measure a construct? Um, you might find this question actually a little strange because if we ask this question in a different context, for example, in daily life, if I ask you, well, how do we measure the length of a table? You would think this is a very easy question because you would say, well, we use a ruler, right, to measure the length of the table. Well, that's exactly actually the kind of answer that I expect to this question. The question, of course, is, well, the difference, of course, is what do we use, first of all, to measure concepts, and the exact manner in which we're going to use the scale, use the ruler, so to speak, to measure the concepts. Because it turns out that there are different rules, there are different principles that govern the measurement of concepts. Okay. Another way to understand this question will be, you know, um, how we can make something that's very abstract to something that's more concrete, such that we can have, more confidence in our observation. Okay, so measurement, specifying research procedures, specifying research rules. So these processes or these components, right, constitute the process that we call operationalization. Okay, so in fact, there are many issues or topics that will fall under this operationalization. It's really a class in itself. But of course, we can't do that. We can't sort of just devote the entire semester to this one single topic. So we are going to focus on one specific issue or one specific topic regarding operationalization, and that is the level at which we will measure a concept. Recall that we just said, right? It's, to measure a concept or to measure a construct is very different from the way that we measure the length of a table. Because, to measure the length of a table, a ruler is pretty much given, right? We just take it and, apply it to the edge of the table, and then we can just get a reading from the ruler, and then we're done. But it turns out that to measure concepts, we have different rules that we have to specify ahead of time, even before we decide to apply any kind of scale, any kind of ruler, quote unquote, to measure a specific concept. And the levels of measurement is one such rule that we must decide prior to our activity of measuring a concept. So, measurement, the noun form of to measure, well, right, is basically, referring to the idea or the process of assigning numerical values to objects. And this is really a very broad concept because obviously, we can measure um, your height, we can measure your weight, we can measure how happy you are, right? So variable is only one of the objects, one of the many objects that we can measure. Um, in general, there are four different levels at which we can measure any particular kind of concept. Or to phrase it in another way, there are four different ways that we can turn a concept into a variable. The first level we'll call nominal measures. The second level we'll call ordinal measures. The third we call interval measures. And the fourth we call ratio measures. Another way to think about or understand these four levels of measurement is to think or to regard these four different measures as four different types of rulers. Each one of them has a specific function, has a different function than the next, right? Each provides some different information, so to speak, about the concept we're going to measure. Okay, so in the next 20 or so minutes, we'll be talking about the properties of each of these measures, starting from nominal, then to ordinal, interval, and then lastly, ratio. Nominal measures. Nominal measures is probably the simplest measure of all that we're going to discuss. When we say we are going to measure a concept nominally, we're essentially saying we're going to break, so to speak, this concept into different categories. We're going to specify all the categories of values that this concept can take. And this will probably remind you of the idea of categorical variables, right? So last week, in probably the second lecture on concept, we said that we have different types of concepts. And a type of concept is categorical categorical variable, or different types of variables, right? And one type of the variables is categorical variables. And we said that, the reason that we call a variable categorical is because the values that the variable takes, are discrete, are, non-overlapping. There are no middle state in between the values they can take, right? They're mutually exclusive, etc. So now we're talking about a process and activity, right, rather than an object. We're saying that one way to measure a variable, one way to measure any variable, is to specify the possible categories of the values that this concept can take. In some cases, this process is very straightforward because, for example, if we're going to measure the biological sex of person, we only have actually, again, in 99% of the time, two categories that we can possibly put all the values into, right? Two categories, in other words, are sufficient to include 99% of the values that this variable biological sex for humans can take. So there are some other typical, measures of that we call nominal, right? So, for example, if we ask people this question, do you prefer PC or a Mac, right? And we give them two choices. This whole thing, right? This whole question plus the answers that we provide is a measure. So here it's very easy to confuse a nominal measure with a categorical variable. So in the context of previous lectures, we'll say that sex in itself, I'm going to choose a different color. sex in itself is very likely, and it's probably true, that it is a categorical variable. So this is a variable. If we just look at, disregard this part, but only look at this one word, then we can say, and correctly so, that this is a categorical variable. But if we see the whole thing, sex, with these two choices, this whole thing on a questionnaire, meaning we are asking people to make a choice when they read this question to indicate whether they're male or female, then we're talking about a measure. See? Let me repeat. If we just look at this word by itself, then we can say, well, biological sex, it is a variable because it can take two values and the two values are discrete, so it's categorical variable. Correct, 100%. But then if we look at not only this word, but also the two choices that follow this word, or another way to think about it is we can easily turn this word into a question. What is your sex? How about that? As such, this entire thing will be very similar to this question, right? Do you prefer PC or Mac? I give you two choices. What is your sex? A question, and I give you two choices. So again, this question plus these two choices together constitute a measure. And because we only provide two values and two non-overlapping values, two discrete values, which do not have any middle state or meaningful middle state in between, we call this measure a nominal measure. We ask people to identify whether they belong to this category or this category, and there are no other choices. Okay? The same thing here, the same idea, right? We ask people a question and they identify themselves belonging to this camp or this camp, and there are no middle ground in this case. They can't say, oh, I prefer PC, 45% of the time, and the rest of the time I prefer Mac. There are no choices provided in this measure, and therefore this is a nominal measure. Okay? So another question is, for example, are you an UHM student? Very easy. Yes or no. There are no middle states, right? It's not a continuum. You either choose this category or choose that category. Again, a nominal measure. It turns out that nominal measure does not mean we can only have two choices. We can have multiple choices, more than two, three, four, five, however many you will like, right? As long as these values are categories of things, but not a continuous state of affairs. So in this case, again, people can either choose one of those, and then sort of categorize themselves into these one of these discrete groupings. So again, the whole thing, right, will be a nominal measure. So you can imagine that this whole thing, a question plus the choices, you can imagine that this is the ruler, right? This is a ruler or tape measure that you use to measure, for example, a person's what do you call it? Their status as a student, right? or their, where they go to school, right? That's a variable, right? Places, the school they attend. This will be, of course, right? This will be a measure, the ruler, the tape measure that we use to index people's brand preferences, right? This is their computer preferences. This is their biological sex. So we use a measure to measure a variable. Again, we use a measure or a scale to measure a variable. The variable here is sort of implicit: computer type, computer preferences. Again, a a measure to measure student status, the variable. A measure, right, the whole thing, a measure to measure a variable that we can call brand preferences. Okay, see the distinction here. All right, so there are several requirements regarding how we can construct a ruler that we call nominal measure. Well, first of all the items, in this nominal measure must be mutually exclusive. And that means, right, well, that's exactly the meaning of it. That is, every observation, that is, if you're going to answer this question, the question, um, you know, in the form of nominal measure, you can only choose one option. There are no both are correct options in a solidly in a well-designed nominal measure. That's what we mean by each observation can only fit into one and only one category. As an example, so imagine, right, Andrew would like to measure people's birthplace. So this is our variable, right, birthplace, because you know people's birthplace definitely differ. So this is a variable. But then the entire question will be a measure, right? The question plus all the choices will be a measure or a scale. Okay, so imagine that Andrew listed the following options. Please indicate your birthplace: Santa Barbara, San Diego, Los Angeles, Southern California, San Francisco, etc. So my question for you is this a good nominal scale? If yes, why it is good. If not, why it is not a good nominal scale. Okay, I'll give you 2 seconds to think about it. If it's not a good nominal scale, what principle does it violate? Okay, I assume that all of you got the answer. This is a bad nominal scale exactly because the choices are not mutually exclusive. The problem is right here. Southern California as a category overlaps, obviously, with Santa Barbara, with San Diego, with Los Angeles, but not with San Francisco, right? So if we just look at Southern California and San Francisco, then the scale will be okay because obviously San Francisco and Southern California, these two are mutually exclusive. But it is not mutually exclusive between Santa Barbara, San Diego, Los Angeles, and Southern California. A person can choose San Diego and choose this option at the same time, or choose Los Angeles and choose this option at the same time. So when a person can choose two categories at the same time, chances are these options are not mutually exclusive. Okay, so that's a problem. We should avoid that. The easy solution, of course, will be to take this out, right? And only, keep the counties, so to speak. So this here is this is the explanation. Okay, you can simultaneously fall in this and some of the other categories. The second criterion of a good nominal scale is that the items not only should be mutually exclusive, but should also be exhaustive. Being exhaustive means it should provide a category to all people, right? Everyone should be able to find a category for themselves. So, for example, right, if you're going to conduct a survey and you would like to know, where people live, right? Then the options you should provide should include all 50 states, right? Not the 48 contiguous states, the mainland states, but also Alaska and Hawaii. We should also single out DC, right? And some overseas possessions, Guam or some other places, right, that America has, such that all people can have a chance of choosing one value. Okay, so this is what we mean by the categories should be exhaustive. So in survey research, and later on, that will be something that you will do as well, is to assign numbers to the categories that we make people choose, right? So for example, when we measure a person's biological sex, we'll say, well, we are going to use 0 to represent male and to use 1 to represent female, or use any other number, right, to represent, for example, we use 1 to represent that you are a UHM student and use 0 to represent that you're not a UHM student, right, etc. The problem, or something that we should all bear in mind, is that numbers in nominal scales do not mean anything at all, right? It doesn't mean that females have more of something than males. It doesn't mean that males are better than females in any possible ways. Um, they're just ones and zeros. They're just random numbers, in other words, that we assign to indicate a specific category. Definitely, as we say here, right? Definitely the numbers do not indicate any sort of ranking. 0 and 1 simply means that these two categories are different. That's it. It indicates difference, but does not indicate any ranking of differences. Okay? They're just labels, in other words, and they're randomly assigned labels. And the reason that we need to assign numbers is because later on when we use Excel, for example, to analyze data, Excel does not really recognize words. They cannot, put words into a formula and produce a number out of it, right? Well, I should say all mathematical formula, including statistics, right? Formula for statistics, they can only handle numbers. They cannot handle words. So that's why we need to conveniently, so to speak, right, to assign some numbers just for the sake of statistical analyses. Okay. All right. So lastly, to repeat the emphasis on the distinction between a nominal measure and a categorical variable. True, right? Categorical variable can only be measured by a nominal measure, right? You cannot use continuous measure, for example, right, to measure people's biological sex. It doesn't make sense to say, well, how much of a male are you? 90%, or how much of female are you? 95%, right? That doesn't make sense at all. And therefore, when we encounter some very classic or typical categorical variables, we can only use nominal measures. So party affiliation, that's another good example. But that does not mean that a nominal measure cannot be used to measure other types of variables, right? So let me repeat. Categorical variables can only be measured by a nominal measure. But that does not mean that a nominal measure can only be used to measure categorical variables, because nominal measure can also be used to measure continuous variables. So for example, if we assume that attitudes toward ice cream or attitudes towards anything is typically treated as a continuous variables, right? We said that usually we use a 7-point scale to measure attitudes, right? Totally against, totally for, or very much dislike, very much like, right? So we typically treat attitudes as a continuous variables, but it's perfectly fine that we use a a nominal measure, dislike, like, to measure attitudes. In other words, we scratch this continuous scale and say that, well, instead of um, assign a very specific number, 1, 2, or 3.5, to people's attitudes, we simply split this group of people into two categories. One category of people, they dislike ice cream, and the other group of people like ice cream relative to the other group of people, right? So that way, we're using a nominal measure or nominal scale to measure what we typically consider as a continuous variable. Oops. Okay. So in the end, we should bear in mind this distinction, right? That I repeatedly try to emphasize. That is, when we say we're handling a nominal measure, then we're talking about a process, a procedure, right? A way to measure variables. We should not confuse a measure with a variable, right? For the purpose, at least for the purpose of this class. So let me repeat. A nominal measure is a process, is an activity, right? In which we measure something, and variable is the object of measurement, right? It's something that we're going to measure. Okay, so bear in mind this distinction, a very important distinction indeed. Okay, so let's move on to talk about a second type of measurement, and this type of measurement we call ordinal measures. Ordinal measures has a very simple definition. It simply means we measure we measure a concept by rank the possible values that it can take. In other words, we will apply a ranking system to a particular concept. So when we talk about rank or ranking, what examples do you have in mind? Right? One example that it's probably classic is the Olympic medals, right? We have, different types of medals. We have gold medal, we have silver, we have bronze, and these are, first of all, right? Let me write it out. We have gold, we have silver, and we have bronze. So first of all, we can immediately see that these three categories actually form, first of all, a nominal measure, right? A person that is, the person has won a gold medal cannot at the same time be awarded with a silver medal. And similarly, someone that, has gained a bronze medal cannot at the same time, obtain a gold medal, right? They're mutually exclusive, they're discrete, there are no other inter-between state between the gold and silver, between gold and bronze, right? They're independent categories. So to be, at the very beginning, um, this is a nominal measure system. But what makes, this nominal measure system actually an ordinal measure or ordinal scale is exactly because they have ranking, right? Compare this gold, silver, medal, bronze with male, female, right? Male, female. These two systems are similar in the sense that they're both categories, right? Male is a category, silver is a category, gold medals is a category, females is a category. But what differs between these two systems, measurement systems, is that we don't have any ranking here, right? It doesn't make sense at all to say that, even by putting male this category ahead of female category, we're implying that male are more important or in any way better than females. That's totally arbitrary. You can easily put females ahead of male, and at the same time indicating no, you know, ranking, right? No preference between these two categories. Um, these categories simply implies difference, right? The difference are not ranked, but very differently from the system. We said that in addition to be categories, gold, silver, bronze, we also can meaningfully rank them, right? Gold is better than silver, silver is better than bronze. That's a rank. Whenever we have a rank or ranking system, this system will constitute an ordinal measure. So ordinal measure, first of all, have just recap, what we just said, right? A mod, sorry, an typo here. An ordinal measure, first of all, will fulfill the same function, will provide the same information as a nominal measure by, you know, uh, distinguishing between different states, distinguishing between different categories, right? That's what a nominal measure can do, and ordinal measure can do the same thing, can distinguish between different groups of sportsmen or sportswomen. But at the same time, an ordinal measure can do something that a nominal measure cannot do, and that is to indicate ranking. We can easily and meaningfully say that silver is better than bronze, and bronze is worse, not as good as gold medal winner. Okay. Um, but at the same time, there's a very important point that we would like to make here, and that is, um, even though an ordinal measure can indicate ranking, the ranking does not contain any information about what we call the differences of degree or the extent to which they're different. Okay, so let me specify and explain what I mean by a ranking variable or ordinal measure does not indicate differences of degree. So let's consider or imagine two dash games. And we know so far the fastest man in this world is Mr. Bolt, right? Winners of Olympic medals, gold medals. And let's say, Andrew is going to have a dash game with Mr. Bolt, and a third person that would join this 100-meter dash game will be Andrew's best friend in graduate school, Doug. Okay, so not surprisingly, in the first game, Mr. Bolt will be the fastest, right? And that's the Mr. Bolt's what do you call it? His performance, right? 9 seconds and 58. Andrew's performance is 12 seconds, 58, and Doug's performance is 13 seconds, 58. So Andrew said, "Well, okay, let's do it one more time, and see, if I can get any faster, or Andrew can get any faster." So they have a second game. So this time, Mr. Bold um, was a little, slower than his first time performance, and Andrew indeed got faster. At the same time, Doug got slower. Regardless, though, the difference between the two performances for each person, 9 second 55 to 9 second 66, 12 second 59 to 10 second 66, 13 seconds 58 to 14 seconds 66, regardless of these minor differences, we still will have Mr. Bold as the gold medal winner, Andrew the silver medal winner, and Doug the bronze medal winner. Okay? So, in other words, if we just look at the kind of medal that Mr. Bolt, Andrew, and Doug win, you will not be able to know the specific performance they have, the specific performance that won them the medals. You will only know that Bolt is faster than Andrew, and Andrew is faster than Doug, but you don't know how much faster. The difference between, in other words, the exact difference between these two performances, you do not know. And certainly, the medals, this ranking system, right? This ranking system itself does not contain these pieces of information, right? We cannot, it's impossible for us to simply infer from looking, at a gold medal to say, well, Mr. Bolt runs this fast, right? We need additional help to record his exact performance. So that's what we mean by differences of degree, right? A 3 millisecond difference, that's difference of degree. A 1 millisecond difference is difference of degree. Sorry, that's a 1 second difference. 3 seconds. And here as well, right? A 1 second difference, that's a difference of degree. A 4 second difference, that's a difference of degree. But all these differences in degrees are not contained, in this medal system, right? So ranking will tells us who's better, but how much better, we don't know. Okay, so that's a very important point that we should bear in mind regarding the properties of ordinal measures. Okay, no, we don't know how much better. We only know that one is better. So, just to reinforce this idea, we assume that we're going to use a this measure, right? Use a use a 1 to okay. So here the example is like this. Okay, we assume that 1 is most delicious. Okay, delicious. And 5 is least delicious. Okay, least delicious. So assume, we have, of course, 2, 3, 4 in between, and we assume that is these five numbers, 1, 2, 3, 4, 5, constitute an ordinal scale. And when, we apply this ordinal scale to Andrew's preference for food, Andrew gave the following answers. So Andrew assigned a 1 to dim sum, a 2 to burrito, a 3 to sushi, a 4 to pizza, and 5 to chow mein. So if this numbering system is an ordinal scale, and based on this information, my question is, can we say a 1 is more delicious than a 2? Can we? We certainly can, because we specified ahead of time, right, to use 1 to indicate a type of food that's the most delicious, and we use 5 to indicate the type of food that's least delicious, and with 2, 3, 4 in between. Okay, so definitely 1 is more delicious than a 2. But can we say that 1 is more delicious than a 2 to the same degree as 4 is more delicious than 5? Can we say that? Think about it. The answer is no. Okay. This is yes. This is no. Why this is yes? Because we know, and we said before, that ordinal measure can tell us the rank. So 1 is ranked above a 2. 1 is ranked above a 2. So we know that 1 is better than 2. But then what an ordinal measure cannot tell us is the differences in degrees. Even though we know that 1 is better than 2, we don't know how much better 1 is compared to 2. For the same reason, we know that 4 is better than 5, but we don't know how much better 4 is than 5. It is possible, for example, in Andrew's mind, 1 is this much better than 2, whereas, 3 is here, 4 is here, and 5 is here, right? This is definitely an ordinal scale because 1 is ranked, okay. Let me redo this. Eraser. Okay, let me redo this. It's very possible that, for example, for Andrew, 1 is ranked so much higher than 2. Whereas, 3, 4, 5 is here, right? 2, 3, 4, 5. So you see that this difference between 1 and 2 is so much larger than this difference between 4 and 5. And it is also possible, equally possible, that we have a reverse situation, right? 1 is still ranked above 2, but it turns out that everything else is or has a very wide margin of difference. So 3 is here, 4 is here, 5 is here, right? So this time the difference between 1 and 2 is much smaller than the difference between 4 and 5. So in other words, both are valid ordinal scales. Both scales satisfy our designation here. 1 is better than 2, 2 better than 3, 3 better than 4, 4 better than 5. But we can specify other details such that these two scales actually mean very different things. And that's why we cannot say with an ordinal scale that 1 is much more better than 2 to the same extent as 4 is better than 5. Okay, I hope this makes sense. Cannot? That's the answer. Okay, so another way to think about it is this. The reason that, okay, another typo, I'm very sorry about that. The reason that we cannot say that 1 is better than 2 to the same extent as 4 is better than 5 is ordinal measures, they have unequal intervals, right? So as we just drew this, right? That's 1 and 2, 3, 4, 5, right? So this is an interval between 1 and 2. This is a second interval between 2 and 3, a third interval between 3 and 4, a fourth interval between 4 and 5. So these four intervals, they're not equal to each other. This is wider, this is narrower, and this is even more narrow. Okay, that's what we mean. All right, here's just another example. And exactly because, for an ordinal scale, right, ordinal. Exactly because for an ordinal scale, we don't have equal intervals. That means we assign different weights to different values on this variable. For example, here, exactly because 1 is so much better than 2, and of course so much better than the rest of the types of food, that implies that Andrew assigns very likely a very heavy weight to dim sum, but a much lighter weight to sushi. And exactly because all these different values have different weights indicated by the different intervals they have, right? We cannot compute means. We cannot compute means from interval scale. In other words, it doesn't make sense to add up 1, 2, 3, 4, and 5, and then divide the sum of these 5 numbers by a 5. That will give you, mathematically speaking, an average number, but this average number does not mean anything at all because different intervals carry different weights. Okay? Okay. What if you ask, what if I have an ordinal measure, and I know that with an ordinal measure we don't have equal intervals, but what if I make those intervals equal? What will happen? Well, if you do that, congratulations, you will have our next type of measures that we call an interval measure. An interval measure is simply an ordinal measure with equal intervals. So again, this time we have a scale for attitudes toward dim sum, but this time I have equal intervals, or assume that the intervals between every two values, between 1 and 2, between 2 and 3, between 3 and 4, the interval between each pair of values are the same. And once we assume that, or once we make sure that happens, we'll have an interval scale. So in this case, with this particular scale, right, a 7 is definitely better than 6. But at the same time, and very importantly, 7 is better than 6 to the same extent as 6 is better than 5. The reason is exactly because these two intervals, right, the interval between 5 and 6 and the interval between 6 and 7 are the same. Okay? And exactly because with an interval scale, we have equal intervals, right? now we can meaningfully compute and interpret means or averages. Okay? However, an interval scale does have a major limitation, a problem. The problem is what we call an arbitrary 0 point. What does it mean? It means with an interval scale, if we ever have a 0 value in it, the value 0 does not mean the absence of something. Rather, the 0 is simply assigned for or to facilitate statistical analysis. This 0 is not a real 0. I know this is very abstract. Right? I had a problem understanding it when I was an undergraduate student like you. So, let's look at an example. Fahrenheit. We know that this is a continuous scale. A scale of temperature definitely is continuous. It has, numbers. It has equal intervals, and we know that 50 degrees Fahrenheit is warmer than 40 degrees Fahrenheit. Okay? But the problem is, we say that the 0 point on the scale, we say it's not a real 0, it's arbitrary, exactly because 0 degree Fahrenheit does not mean the absence of temperature. Rather, it simply is the lowest temperature that Mr. Fahrenheit could produce chemically. That's it. Imagine Mr. Fahrenheit in a different mood on that day said, well, let me use 1 degree of Fahrenheit to indicate the lowest temperature that I could synthesize or I could produce chemically. If that's the case, if Fahrenheit made a very arbitrary but different decision, using 1 degrees of Fahrenheit instead of 0 degrees Fahrenheit as the lowest temperature he could produce, then today we'll have a very different Fahrenheit scale than what we actually have. Right? So this is what we mean by saying that, an interval scale like the Fahrenheit scale is an interval having an arbitrary 0 point. Right? So in this case, it could easily have, a very different system treating 10 as the lowest temperature. Okay? And if he did that, right? So this is the Fahrenheit scale that we have nowadays. But if, let's imagine, right, he treated 10 degrees Fahrenheit instead of 0 as, the lowest temperature that he could produce chemically, what this scale might look like. In other words, instead of having 0 here, we replace 0 with 10. Then what else should we change? All right? That means we'll simply add 10 to each of these values. 10 will become 0. We add 10 to 20, will become 30. We add 10 to 40, becomes 50. And we add 120, we get under 30. Okay? But still, we know that 130, this degree, this temperature is warmer than this temperature. And we still know that this temperature is warmer than this temperature to the same extent as this temperature is warmer than this temperature. Nothing's changed, Numbers changing, but the meaning or the information that this new Fahrenheit scale provides remains the same. Okay, and this is due to the 0 being arbitrary. Okay, so let's see if we really understand this, arbitrary 0 point on an interval scale. So I give you here the original or the, usual Fahrenheit scale, starting with 0. We know from the previous discussion that, 20 degree Fahrenheit is 20 degrees higher or warmer than 0 Fahrenheit degree. That we can say, right? And we can also confidently say that 40 degree Fahrenheit is also 20 degrees warmer or higher than 20 degree Fahrenheit. So far, so good. But my question for you is, can we say that 40 degrees Fahrenheit is twice as warm as 20 degrees Fahrenheit? Can we say that? Why or why not? Right, there's only one correct answer. You can either say, yes, we can meaningfully say 40 degrees Fahrenheit is twice as warm as 20 degrees Fahrenheit, or you can say, no, we cannot meaningfully say that. Which one would you choose? And what's your reason? Okay, I give you 2 seconds to think about it while I take a sip of water. Okay, here's the answer. Answer is you cannot. You cannot meaningfully say that 40 degree Fahrenheit is twice as warm as 20 degree Fahrenheit. The reason is exactly because we have an arbitrary 0 point. So with this particular scale that has 0 as the starting point, we could say that 40 degree Fahrenheit is twice as warm as 20 degree Fahrenheit because, 2 times 20, that's 40. So with this particular scale, we could say that. But imagine we replace this arbitrary 0 point with 10 degree Fahrenheit. We could do that because 0, as we said, is arbitrary, right? It does not mean the absence of temperature. It simply means a certain lowest degree, a certain low temperature, right? We can easily define this low temperature as 10 instead of 0. But if we do that, if we add 10 to 0, and as we saw before, we need to add 10 to every and each following values. So 20 became 30, 40 became 50, all the way to 120 became 130. Now, 20 degree Fahrenheit on this scale becomes 30 degrees Fahrenheit on this scale, and 40 degrees Fahrenheit on this scale becomes 50 degrees Fahrenheit on this scale. And certainly 50 degrees Fahrenheit is not twice as warm as 30 degrees Fahrenheit. Because 2 times 30 is 60, not 50. Make sense? Okay. This example is, may take some time for you to digest, but I laid out every step, every reasoning step here. So if you don't still have a little bit of difficulty of understanding it, which is perfectly fine, just read the slides, several times, and of course, welcome to ask me if you still think that you need a little bit of help. right? To understand this question. Okay, so in the end, we say that the fundamental reason is zero is arbitrary, right? Does not mean the absence of something. Lastly, we have ratio measure, and ratio measure simply is to provide a meaningful, not an arbitrary 0 point to an interval measure. Okay, so an example would be income. When you have a 0 on the scale for income, the 0 here is not arbitrary. It simply means, and it certainly means, that you don't have a dime, right? You don't have any money in your pocket. So this is a real 0. And exactly because the 0 is real, then you can say, meaningfully say, that $4 is twice as much as $2. And if you earn $4 and I earn $2, you can meaningfully say that you are twice as rich as Andrew. Okay? The reason here is you have a meaningful 0 point. You cannot change, consequently, on the scale to another system. Right? You cannot add 1, for example, to 0, because once you add 1 to 0, the meaning of this number will change. It will never mean that you don't have any money. Instead, it will mean you have $1 or 1 cent, right? Which is very different from you don't have a cent or you don't have any money, right? That means you cannot arbitrarily shift numbers around to make the same scale, to make the new scale provide the same information. Once you add numbers to the 0 point, you add numbers to all the following points, and the meaning of the scale and the meaning of the entire scale would change. Okay? So, simply speaking, don't mess with ratio measures. Okay? All right. So now we have talked about the 4 levels of measurement, and we can think actually the 4 levels of measurements as steps. At the lowest level of the step, we have a nominal measure. Nominal measure, and with nominal measure, we know that attributes or categories are named. Right? We only specify the categories. We only name, well, you're a woman, you're a man, you're a UHM student, you're not a UHM student. Right? We name the attributes. A step up, we have ordinal measures. With ordinal measures, we not only name attributes, but the attributes are ranked. And then we have interval measures. The improvement of interval measures from ordinal measures is that now we rank attributes on equal intervals. Right? Recall, with nominal measures, we don't have equal intervals, but with interval scales, we have equal intervals or equal distance. Lastly, at the highest level, we have ratio measure. Ratio measure here is we add a true 0, a non-arbitrary 0, to this equal interval scale. And all these constitute the 4 levels of measurement. The 4 types of scales that we can use to measure the variables that we're interested in. Okay, so I will give you this brief exercise. All right? Consider the variable that you are interested in is Andrew's attitudes toward ice cream. So this is a variable, right? Andrew can have different attitudes toward ice cream. Now, the exercise, which would not be graded simply for your practice purpose, is to construct a nominal an ordinal, and an interval scale or measure to measure the same concept. You measure the same concept with 3 different measures. How would you do it? Okay, so this will conclude this lecture on measurement or operationalization, and we'll see you tomorrow.